Manchester, New Hampshire. The 15th of October, 1891. About 9:30 in the morning. Inside the brick canyon of the Amoskeag Manufacturing Company, the sound never stops. Thousands of leather belts snap and hum overhead. Looms clatter in long rows. Carding machines tear raw cotton into even webs of fiber. Somewhere below all of it, in a pit on the ground floor of Mill Number 7, a 30-foot cast-iron flywheel turns and turns, driving the machinery of 4 separate mill buildings through a single main shaft. That morning, something is wrong with the power. Superintendent Marcellus Gould has been fielding complaints since the shift began. On the south side of the yard, carding machines are starving for power, slowing down as if the whole system were running out of breath. On the north side, looms are doing the opposite, speeding up, some of them dangerously, forcing operators to shut them down before they tear themselves apart. Gould goes looking for the man who understands the power plant better than anyone, engineer Samuel Bunker. He asks him what's going on. Bunker isn't sure. He says he'll go find out. Then he walks toward the engine room and climbs down into the pit that houses the flywheel. He does not walk back out. Within moments, the floor above the pit gives way. Metal tears through timber and brick. Steam roars into the wreckage. 3 people will die before the day is over. 8 more will be carried out injured. A machine that had spun reliably year after year, powering a mill complex that helped define industrial America, has destroyed part of its own engine house in what witnesses will remember as an instant. How does that happen? How does a wheel that turned so slowly you could almost count the revolutions, a wheel that had done its job without complaint for the better part of a decade, come apart with enough violence to throw iron fragments across a river? That question would occupy engineers for months. In some ways, it's never been fully answered. This is the story of the Amoskeag flywheel disaster, one of the deadliest industrial accidents in New England's manufacturing history, and one of the strangest engineering mysteries of its era. We're going to look at the machine itself, the enormous Corliss steam engine known at the mill as the Big Jumbo, and the 30-foot flywheel that turned beside it. We're going to look at the workers who kept that system running, the warning signs that appeared in the hours before the failure, and the physical destruction that followed. We're going to look at what investigators found afterward, and, just as importantly, what they couldn't determine because the exact sequence that caused this flywheel to come apart was never conclusively established. It's worth pausing on the language here, because the accident is often remembered as an explosion. That's the word the newspapers used in 1891, and it's the word that stuck. But nothing burned or detonated inside that engine room. What failed was a rotating mass of cast iron, spinning under enough stress that it tore itself apart and released its stored energy all at once. The word explosion describes what it felt like to the people standing nearby. It doesn't describe what actually happened inside the metal. There's a contradiction buried in the middle of this story, and it's one investigators struggled with for months afterward. In the hour before the failure, machinery on one side of the mill complex was slowing down from a lack of power, while machinery on the other side was speeding up past safe limits. 2 opposite symptoms happening at the same time from what should have been a single, steady source of power. What could cause a system to fail in 2 directions at once? The answer, as we'll see, was hiding in the way power moved from that flywheel out into the mills and in the broken metal itself once engineers finally got a chance to examine it. To understand why a single machine failure could kill 3 people and injure 8 more, you have to understand what the Amoskeag Manufacturing Company actually was. This wasn't a factory in the way we might picture one today. It was closer to an industrial city built around a waterfall. The company took its name from Amoskeag Falls, a 50-plus foot drop on the Merrimack River where the water had drawn fishing communities for centuries before any mill was built. In the early 1800s, entrepreneurs recognized what that falling water could do, and by 1831, the Amoskeag Manufacturing Company had been formally incorporated in New Hampshire. From there, it grew at a pace that reshaped the whole region, The company didn't just build mills, it laid out the street grid of Manchester itself, sold house lots to residents, built worker housing, and effectively planned the city around its own industrial needs. By the final decades of the 19th century, Amoskeag had become one of the largest textile manufacturing operations in the world. Eventually, the complex would include roughly 30 major mill buildings, stretching for more than a mile along both banks of the Merrimack, employing thousands of workers drawn from New England farms and from immigrant communities across Europe and Canada. At its peak, in the years around the First World War, the company's payroll would swell past 17,000 people. None of that scale was possible without dependable centralized power. A textile mill isn't just a building full of workers, it's a building full of machines that all need to move in a coordinated, continuous way. Looms need steady tension. Carding machines need consistent speed to produce even fiber. Spinning frames need power that doesn't surge or stall, because either one ruins the product and endangers the people standing next to the machinery. For decades, Amoskeag met that need with the river itself, using dams and canals to deliver water power directly to line shafts, running the length of each mill. But water power had a weakness. The river wasn't always cooperative. Low water in dry seasons meant less power available exactly when the mills needed it most. So, by the 1880s, Amoskeag had supplemented its water power with something newer and more concentrated, a massive steam engine built to deliver power on demand regardless of what the Merrimack was doing that week. This engine, and the enormous flywheel connected to it, became responsible for driving the machinery inside mills 4, 5, 7, and 8. 4 separate buildings, all drawing power from one rotating shaft. That's the detail worth sitting with. 4 mill buildings, hundreds of machines, thousands of individual tasks being performed by workers at every level of the complex, all of it ultimately depending on one engine and one wheel, turning steadily in a pit most of those workers never saw. The workforce that filled those buildings was, by the 1890s, remarkably diverse for its era. Amoskeag drew laborers from New England farm towns, from French-Canadian communities to the north, and from waves of Irish, German, Greek, and Polish immigrants arriving through the later decades of the century. Many lived in company-owned tenement housing built specifically to keep workers close to the mills, paying rent directly to the same company that employed them, and, in many cases, employed several members of the same household at once. That closeness meant something specific on a day like the 15th of October, 1891. When something went wrong in one building, workers with relatives or friends elsewhere in the complex often heard about it within minutes and came running to find out who had been hurt. It's worth remembering, too, that factory work in this period was already understood to be dangerous in smaller, more routine ways: caught fingers, crushed hands, the everyday hazards of operating heavy machinery for 10 or more hours a day. What made October 15th different wasn't the presence of danger. It was the scale of a single failure, striking not one worker at one machine, but reaching into the structural core of the building itself. The steam engine at the heart of this story was a Corliss engine, a design that by 1891 had already earned a reputation as one of the great achievements of American mechanical engineering. Corliss engines used a distinctive valve system, patented by Rhode Island engineer George Corliss decades earlier, that opened and closed with far more precision than older slide valve designs. That precision meant less wasted steam, more consistent power delivery, and significantly better fuel efficiency than conventional engines of the period. A Corliss engine had famously powered the entire 1,876 Centennial Exhibition in Philadelphia, and by the time Amoskeag installed its own version in 1883, the design was considered the gold standard for large-scale industrial power. Even with that precision, though, a steam engine has an inherent problem. It doesn't deliver power evenly. A piston moves back and forth, pushed by steam entering and leaving a cylinder in a repeating cycle. Power peaks and dips with every stroke. Left on its own, that unevenness would translate directly into machinery looms jerking, spindles surging and slowing, cloth coming out uneven or torn. Manufacturers needed a way to smooth that pulsing power into something steady enough to run thousands of delicate operations at once. That's the job a flywheel does. A flywheel is, at its simplest, a very heavy wheel attached to a rotating shaft. Because of its mass, it resists sudden changes in speed. When the engine delivers a burst of power, the flywheel absorbs the extra energy and speeds up only slightly. When the engine's power dips between strokes, the flywheel gives some of that stored energy back, keeping the shaft turning at a nearly constant rate. The heavier the wheel and the farther that mass sits from the center, the more effectively it smooths out the engine's pulses. That's why industrial flywheels of this era were built enormous, not for show, but because size and mass were exactly what made them useful. At Amoskeag, that principle was taken about as far as it could reasonably go. The flywheel connected to the mill's Corliss engine was roughly 30 feet in diameter, large enough that a person standing beside it would have looked small next to the rim. From that wheel, power moved outward through wide leather belts, some reported to be more than 3 feet across, running from the flywheel's rim to shafts that in turn drove the machinery inside the connected mill buildings. It was, in effect, a mechanical relay: steam engine to flywheel, flywheel to belt, belt to shaft, shaft to machine, repeated hundreds of times over across 4 buildings. Here's the part that made this system both powerful and dangerous. A rotating mass doesn't just carry the energy you can see in its motion, it stores energy in a way that scales dramatically with speed. A wheel spinning twice as fast doesn't store twice the energy. It stores roughly 4 times as much, because kinetic energy in a rotating object increases with the square of its velocity. A wheel with most of its weight concentrated in a heavy outer rim, spinning at even a modest number of revolutions per minute, can therefore be carrying an extraordinary amount of stored mechanical energy, energy that has nowhere obvious to go unless something forces it out. Under normal operation, that energy simply flows through the belts and shafts, doing the work it was designed to do. But cast iron, the material used for flywheels like this one, has a specific vulnerability. It's very strong under compression, it resists being crushed, but it's much weaker under tension, the kind of stretching, pulling stress that a rim experiences as it spins. And cast iron is also unforgiving of internal flaws. Tiny gaps, air pockets, or irregularities left behind during the casting process can act as starting points for cracks, concentrating stress in ways invisible from the outside. A flaw that might sit dormant for years under normal load can, under the right combination of speed and stress, become the place where the entire structure gives way. None of that was visible to the workers at Amoskeag going about their morning. To them, the flywheel in the pit beneath Mill Number 7 was simply part of the building, a fixture that had been turning reliably for years. It looked steady. It sounded steady. Whatever stress was building inside the iron itself, whatever flaw might have been sitting quietly in the casting since 1883, gave no outward sign. That's the unsettling truth at the center of this story. The machine that was about to fail catastrophically looked, right up until it didn't, exactly like a machine that was working fine. By most accounts, the morning of the 15th of October 1891 started like any other at Amoskeag. Workers were at their stations in Mills 4, 5, 7, and 8, running looms and carding machines under the power delivered from the big jumbo engine and its flywheel. Then the power began behaving strangely. On the south side of the power plant, carding machines started slowing down, as though they weren't getting enough force through the shaft to keep pace. On the north side, the opposite was happening. Looms were speeding up, some reaching speeds fast enough that operators had to shut them down before the machines damaged themselves or the fabric running through them. According to a later account, at least one loom's automatic shutoff mechanism failed to engage, and the machine ran at a pace no one on the floor had seen before or would see again. This is the contradiction we mentioned earlier, and it's worth sitting with because it's genuinely strange. A single shaft, turning at a single speed, was somehow delivering less power in one direction and more power in another at the same time. That's not what a healthy, uniform power system is supposed to do. Something in the transmission, not necessarily the flywheel itself, but the belts, couplings, or gearing connecting it to the shaft, appeared to be behaving inconsistently. Superintendent Marcellus Gould, an experienced mill manager who had worked at manufacturing facilities from New Hampshire to Connecticut before coming to Amoskeag, went looking for answers. He found engineer Samuel Bunker and asked him what was happening with the power. According to accounts recorded in the aftermath, Bunker's reply was brief. There was nothing he knew of, but he would find out. With that, Bunker headed toward the engine room to investigate the pit where the flywheel and its connecting machinery were housed. Gould was not a man inclined to panic over a minor mechanical hiccup. He had built a career troubleshooting mill operations at facilities across New Hampshire and Connecticut before coming to Amoskeag, and he had a reputation for a practical eye when it came to machinery and production. If the erratic power that morning had seemed like an ordinary minor fluctuation, it's unlikely he would have gone looking for Bunker personally. The fact that he did suggests the problem, whatever it was, felt different from the usual small inconsistencies of a working mill. Gould, meanwhile, turned to walk back through a connecting tunnel toward mill number 5, where the slowdown in the carding machines had been most noticeable. He had made it partway along that tunnel. Accounts describe him as roughly halfway through it when the flywheel failed. Consider what each of these two men was doing in that final stretch of ordinary time. Gould was walking away from the engine room, back toward the machines that had first alerted him something was wrong. Bunker was walking toward the source of the problem, into the one place in the entire complex where the true condition of the flywheel could actually be seen up close. Neither man had any way of knowing that the wheel itself, not just the belts or the shaft or the machinery downstream, was approaching the end of its ability to hold together. According to a later account, in the moments just before the failure, an assistant engineer looked through a window into the engine room and saw the flywheel turning at a speed well beyond what was normal, with sparks visible along the wide main belt that connected it to the shaft. The assistant was reportedly in the process of trying to cut power to the engine when the wheel came apart. Samuel Bunker was in the pit at that moment. He did not come back out. The wheel gave way. Cast iron does not bend before it breaks. It fractures. And when a rotating mass carrying that much stored energy loses its structural integrity, the pieces don't simply fall, they're flung outward, carrying the velocity they had at the rim of the wheel an instant before. What had been smooth, continuous rotation became, in a fraction of a second, a scattering of iron traveling in whatever direction physics and geometry allowed. There was no gradual buildup that anyone on the mill floor could have reacted to. One moment, the machinery was running under the same erratic, uneven power that had puzzled Gould and Bunker all morning. The next, the source of that power was tearing itself apart. The sound came first. Witnesses would later describe something like an explosion, the noise of metal tearing, timbers cracking, and the structure of the engine room giving way almost simultaneously. It was loud enough and sudden enough that people in buildings well away from mill number 7 understood immediately that something had gone catastrophically wrong, even before they knew what. Then came the aftermath: falling beams, collapsing sections of floor, and steam venting violently from the ruptured engine. The engine house itself, built to contain and support the machinery inside it, was not built to withstand a multi-ton mass of iron breaking apart at speed. Sections of the structure gave way along with the machinery, turning what had been an enclosed engine room into an open, debris-strewn space in a matter of seconds. Fragments of iron, some reportedly weighing close to 1,000 pounds, were thrown through the surrounding structure and beyond it. One large piece of debris was reportedly launched roughly 200 feet into the air before crashing back down through the roof of mill number 7. Other fragments tore through windows in neighboring buildings, showering nearby workers with broken glass. Some pieces were reportedly found on the far side of the Merrimack River. Directly above the pit, on the second floor of Mill Number 7, a crew of 11 workers had been going about their morning. When the wheel failed, the floor beneath them gave way. They dropped to the ground level amid falling beams, broken machinery, and debris. One survivor's account, recorded afterward, describes what that fall was like from the inside. Lemuel Levick, who had been working on that second floor, later described dropping straight down as the floor collapsed, with a nearby cupboard falling beside him and forming a pocket of shelter amid the wreckage. Outside that shelter, steam continued to vent into the ruined engine room. Levick reportedly saw a mill girl being scalded by the steam nearby and pulled her into the space with him until rescuers were able to reach them both. In the pit itself, engineer Samuel Bunker did not survive the initial failure. He had gone down to investigate a problem he didn't yet understand, and the machine he was inspecting had come apart around him before he had time to report back. The noise of the failure carried through the mill complex immediately. Workers in neighboring buildings, many of whom had friends or family working elsewhere in the same complex, rushed toward Mill Number 7 to find out what had happened and who had been hurt. In the first minutes after the collapse, no one on the scene would have known the full scope of the damage, whether the failure was confined to the engine room, whether other parts of the building were structurally sound, or how many people were trapped beneath the wreckage. That uncertainty, as much as the physical destruction itself, defined the chaotic first stretch of the response. As rescuers worked to free the injured from broken timbers and twisted machinery, while steam continued to escape from the ruptured engine. What they found, as the immediate confusion settled, was a wrecked engine room, a partially collapsed floor, injured coworkers being pulled from the debris, and a stillness where, moments before, there had been the steady hum of a machine that had run without incident for years. 3 people died as a result of the Amoskeag flywheel disaster. Their names, as recorded in the coroner's jury verdict taken on the day of the accident, were Samuel J. Bunker, Ada L. Cram, and Mary Kane. That spelling matters because it isn't consistent across every account of this story that survives. Some later retellings render the second victim's name as Ida rather than Ada. The official coroner's jury document, however, an inquisition taken in Manchester on October 15, 1891, before Coroner Harrison D. Lord records her name clearly as Ada L. Cram, and that spelling is corroborated by a family descendant who has identified her as a great-aunt, a woman remembered within her own family as Ada. We've followed the primary record and that family confirmation here. Similarly, while some accounts have rendered the third victim's surname as Kane, the coroner's jury verdict records her name as Mary Kane, and that is the spelling used in this account. Samuel Bunker was the mill's engineer, the man responsible for understanding exactly the kind of problem that appeared that morning. He went into the pit to investigate an unstable power delivery and was killed when the flywheel he was likely inspecting came apart. Ada Cram suffered severe injuries in the collapse and reportedly died from a head injury after being brought to a nearby hospital. Mary Kane, reported in some accounts to have been around 21 years old, died from a severe injury sustained in the disaster. Beyond the 3 fatalities, 8 other workers were injured, described in period accounts as suffering broken bones and other serious injuries. One report from the time mentions a 12-year-old boy among those hurt, a detail that says something uncomfortable but important about who worked inside mills. Like this one in 1891. Child labor was not unusual in New England's textile industry at that time, and photographs taken at Amoskeag less than 2 decades later would document children as young as 11 or 12 still working the floor. What's striking, looking back at the record now, is the imbalance in what survived. We have precise measurements of the flywheel, its diameter, its estimated weight, the width of its main drive belt. We have technical descriptions of the engine, the shaft, the transmission system. We have almost none of that same detail about the people who worked around those machines every day. We don't know what Mary Kane's daily routine looked like, what Ada Cram's family situation was beyond a single relative's memory generations later, or what Samuel Bunker had done in the years before he became the engineer responsible for the mill's power plant. The industrial record of 1,891 was built to preserve information about machines. It was not built with the same care to preserve information about the people who operated them. That's not a criticism we can resolve from a distance of more than a century. It's simply the shape of the evidence that survives, and it's worth naming plainly, rather than filling in with invented detail. In the aftermath of the disaster, a coroner's jury was convened in Manchester to examine what had happened. According to the surviving verdict, the jury, including Justice of the Peace Jacob F. James and jurors Nehemiah S. Bean and James P. Tuttle, found that Bunker, Cram, and Kane had died from injuries caused by the failure of the 30-foot flywheel while it was in operation in the Amoskeag engine room. The jury's findings did not attribute the failure to wrongdoing on the part of the company or the engineers who operated the machinery. Separately, engineers examined what remained of the shattered flywheel to try to understand why it had failed. What they found in the recovered iron was troubling but not conclusive. Irregularities in the casting, including small gaps or voids left behind from the original manufacturing process, the kind of flaw that could act as a weak point under stress. It's tempting, looking at that finding, to treat it as the obvious answer, a defective casting, finally giving way after years of hidden strain. But the investigators themselves were more cautious than that. The engine and flywheel had operated for roughly 8 years without any sign of trouble. If a casting flaw alone were enough to cause catastrophic failure, it's reasonable to ask why the wheel hadn't failed sooner. The most defensible conclusion investigators could draw was narrower. The casting irregularities likely weakened the wheel and made it more vulnerable to failure without necessarily being the single triggering cause on their own. So what else was in play? This is where the contradictory power behavior from that morning becomes central to the investigation rather than just a strange detail. Remember, carting machines to the south of the power plant were slowing from inadequate power, while looms to the north were speeding up dangerously at the same time from the same shaft. The explanation investigators considered most plausible involved the mechanism connecting the flywheel's drive belts to the shaft that distributed power north and south to the different mill buildings. If that connecting mechanism had begun to fail gradually, perhaps a slipping or loosening in the coupling, the belts on one side could have started to slacken. A slackened belt slipping against its pulley generates friction and heat without efficiently transmitting power, which would explain reduced power reaching the carting machines to the south. As operators or the automatic system responded by trying to push more power through, the mechanism could have intermittently caught and re-engaged with more force than before, sending a surge of power through the belts on the opposite side, which would explain the looms to the north, speeding up past safe limits. A repeating cycle of slipping and catching, worsening over time, could plausibly account for both the slowdown on one side and the dangerous overspeed on the other, all originating from a single failing connection point rather than two separate problems. If that cycle continued to worsen, each catch striking with more force than the last, the cumulative stress on the belts, the shaft, and ultimately the flywheel itself could have built toward a breaking point. Combined with a casting flaw already weakening the iron from within, that escalating mechanical stress offers a coherent, if not fully provable, explanation for why the wheel gave way that particular morning rather than any other day in its 8 years of service. It's important to be honest about the limits of this explanation. The engineers who examined the wreckage in 1891 did not have the diagnostic tools engineers would have today, and the men who might have offered the clearest first-hand account of what was happening inside that pit, most notably Samuel Bunker himself, did not survive to describe what he found. The coupling failure theory was, by the engineer's own admission, their best reconstruction based on incomplete evidence, not a conclusively proven mechanism. No single, universally accepted account of the precise trigger for the failure has come down to us. What we have instead is a plausible, evidence-based theory, sitting alongside an unresolved question about exactly how a casting flaw, a failing mechanical coupling, and years of ordinary operation combine to produce one catastrophic morning. In the wake of the disaster, Amoskeag had a practical problem to solve. 4 mill buildings had depended on that engine and flywheel for their power, and idle machinery meant idle production. The company moved to restore power to the affected mills, addressing the immediate damage to the engine room and the destroyed flywheel so that operations could resume. Here, it's important to be precise about what the historical record actually supports. Company histories from the period reference the aftermath of the flywheel disaster and the coroner's findings, but the specific material, dimensions, and construction details of whatever flywheel replaced the shattered one are not something this account can independently verify from reliable sources. Rather than guess at specifications that can't be confirmed, it's worth simply acknowledging that gap. What we can say with confidence is that Amoskeag continued operating its centralized steam power system for years afterward. This was a repair and replacement of the failed component, not an abandonment of the underlying approach to powering the mills. That basic approach, one enormous, centrally located power source feeding machinery across multiple buildings through shafts and belts, didn't disappear because of this one accident. It disappeared gradually, over subsequent decades, for reasons that were more technological and economic than regulatory. Electric motors, which could be sized to individual machines or small groups of machines rather than routed through a single massive shaft system, offered manufacturers flexibility that centralized steam power never could. A factory using distributed electric motors didn't need every machine on the floor tied to the failure risk of one giant rotating mass. If a single motor failed, it took down that motor's machines, not an entire building's worth of production, and certainly not 4 buildings at once. There's something worth noting about the pace of that change. It didn't happen overnight, and it didn't happen because of a single dramatic accident forcing everyone's hand. Large steam-powered mills across New England continued operating centralized systems similar to Amoskeag's for years, even decades after 1891. Change, when it came, arrived gradually mill by mill, replacement by replacement as electric motors became cheaper, more reliable, and more practical to install than the older belt and shaft systems they eventually displaced. Industry-wide, the shift away from systems like the one that failed at Amoskeag was also shaped by a broader wave of engineering caution around large flywheels generally. Insurance companies and industrial engineers increasingly scrutinized flywheel design, casting quality, and containment in the years following high-profile failures like this one. That doesn't mean the Amoskeag accident single-handedly produced new laws or a nationwide regulatory overhaul. The surviving historical record doesn't support that strong a claim. What it does support is a more gradual pattern. Incidents like this one added to a slowly accumulating body of engineering caution, insurance pressure, and design improvement that, combined with the rise of electric power, eventually made giant centralized flywheel systems a rarity rather than the standard. By the time Amoskeag itself closed for good in the mid-1930s, done in by a combination of economic pressure, aging infrastructure, and a changing textile industry, the entire model of power delivery that had defined its mills for a century, water and steam, driving shafts and belts across buildings, had already been superseded elsewhere by electricity. The flywheel disaster of 1891 was not the reason for that larger shift, but it stands as one vivid, costly illustration of exactly the kind of risk that shift eventually left behind. There's a meaningful difference between designing a machine so that engineers believe it won't fail and designing a system so that when failure happens anyway, the people nearby survive it. The Amoskeag flywheel had been engineered to the best standards of its era. It came from a design tradition associated with real technical achievement, installed by a company with every incentive to keep its workers safe and its production running. And it still failed catastrophically, after years of apparently normal operation, in a way that no one on the factory floor could have anticipated from watching it turn. That's not a story about careless engineering. It's a story about the limits of confidence in any single system, no matter how well built, especially one storing enormous amounts of energy in a form that looks calm from the outside. The broader engineering lesson that would slowly take hold across many industries in the decades after accidents like this one wasn't just build stronger wheels, though better casting standards and materials certainly followed. It was a shift in thinking about failure itself, designing systems with containment, redundancy, and safe failure modes in mind, so that when something does eventually give way, the energy it releases doesn't have to travel unchecked through a crowded workspace. That principle didn't originate at Amoskeag alone, and it's not accurate to say this one accident invented modern safety engineering. But it belongs to the same long, uneven history that produced it a history built, disaster by disaster, out of exactly this kind of hard-earned evidence. Today, the Amoskeag mill yard still stands along the Merrimack River in Manchester, though its role has changed completely. The mill buildings that once employed thousands of textile workers now house offices, biotechnology companies, restaurants, and a museum dedicated to the history of the site itself. The Merrimack still runs past the same falls that first drew industry to this stretch of river 2 centuries ago. The engine pit where Samuel Bunker died, the flywheel he went to inspect, and the machinery it once drove are long gone. But the ground they stood on is still part of the working city that Amoskeag itself effectively built. Picture it one more time. Samuel Bunker, told there was a problem with the power he couldn't immediately explain, saying simply that he'd go find out. Walking down into a pit to look at a machine that had been turning steadily, without complaint, for 8 years. A wheel that looked, in that ordinary morning light, exactly like it had looked every other morning before it. That's the detail worth sitting with, more than the wreckage, or the debris field, or the injury count. The historical record kept remarkably precise measurements of that flywheel, its diameter, its estimated weight, the width of the belt running from its rim. It kept far less about the man who walked toward it that day, or the 2 women working elsewhere in the mill whose names we can only now confirm with confidence. That imbalance says something true about how industrial history gets written, and about whose stories survive it intact. A machine can run safely for years and still be carrying, somewhere inside it, exactly the kind of quiet flaw that a long, safe history does nothing to rule out. 8 years of reliable operation told the workers at Amoskeag that the flywheel could be trusted. It told them nothing about what was happening, slowly and invisibly, inside the iron itself. That's not a comfortable thought. It's just an accurate one, and it's the reason this story, more than a century later, still has something to teach anyone who works around large, powerful, apparently trustworthy machines. If there's another forgotten factory disaster or industrial accident you'd want investigated like this one, let us know in the comments.